from the fluttering of the wings of a moth that they are after. So there are a lot of signal processing applications, and I'll blurt out the buzzwords as we go through this video. Let's see.
Flight and the ability to catch insects on the wing is an extraordinary achievement. How do the bats do it?
That's David Attenborough, by the way.
This is a great place for bats. There are a lot of insects flying around. At the moment, birds are feeding on them, and bats are asleep in their roosts. But soon it'll get dark, and then the birds will go to roost, and the bats will come out to claim their share. Now, at night, there are even more flying insects than there were during the day. And down by the mill stream, there's a colony of Dor Benton's bats that are already stirring. Their little faces are so like a shrew's that it's easy to imagine shrew-like ancestors in the trees, jumping from branch to branch, chasing insects. Ever larger flaps of skin between their fingers help to extend those jumps until, eventually, they could fly. And how they can fly. The change from a scurrying animal like a shrew to a fluttering bat is surely the most magical in the whole history of the mammals. The bat's mastery of flight is so complete that few insects can outmaneuver them in the air. The bat scoops up the moth with the membrane around its tail and then passes it forward to the mouth. Their ground-living ancestors probably used sound to find their way through the nighttime forests, as shrews still do. But bats then perfected that technique, using sound frequencies beyond our hearing. A bat detector makes those calls audible to us.
So right there is an application of signal processing where you have audio signals that we can't hear, and we somehow have to detect them and convert them down to a frequency range that our ears can hear. So all these chirpings that you hear, they're not the actual sounds of the bats, they are the converted sounds of the bats. And a bat detector is a signal processing device that does exactly that does the frequency conversion.
Bats emit high-intensity pulses of sound and then listen to the echoes that bounce back.
So what human-engineered system is like that? Sonar or radar. Sonar is for the sound signals, and radar is for electromagnetic signals.
Their brains then process these reflections to give them a three-dimensional image of their surroundings and their prey. Moths, with their rather laborious flight, are relatively easy to catch. But then some evolved a defense, a simple ear, so that when they hear the sonar of the bat approaching, they can swerve out of the way.
And those of you drivers, what's that device called? A what? A what? Radar detector. So these moths have the sonar detector. Okay, there's signal processing all over this clip.
So one bat changed tactics. The long-eared doesn't hunt with sonar. It uses its enormous ears to listen for prey. It can even filter the faint sound of a moth's wing beats through the noise of the rushing water. Its sonar guides it through the branches, but as it approaches the moth, it turns that off and enters stealth mode. Now it's guided solely by the noise of the moth's wing beats. But the system isn't perfect. The bat can hear the moth through the leaf, and it's approaching it from the wrong side. Escape for the moth. But now the bat has come round to the other side. If the moth stays still, it doesn't make any noise at all, so the bat can't locate it. Sooner or later, the moth will have to move. That is its undoing. But how can catch prey that is silent?
I told you you're missing out when you don't see him in the Planet Earth series. So this segment highlights one method of signal processing, which I would call passive sonar or passive radar, where you don't actually send out signals, you just listen. And you'd expect that in such a mode of detection would be more error-prone to an active mode of radar or sonar, where you actually send out signals and listen for reflections. And this also exists. This difference in error rates exists in man-made systems as well.
In a place like this, which is so cluttered with vegetation, that echolocation shouldn't work. These places are difficult to navigate, but they are full of food. Spiders are more nutritious than moths, but they are silent, venomous, and construct webs that are so strong that a bat could easily become fatally entangled in the sticky silk. Here comes Natura's bat. It seems well aware of the almost microscopically thin silken threads, and with surgical precision removes the spider from its web.
This guy uses active sonar. Because you can't make the kinds of mistakes that the long-eared bat was making.
It even reverses away from the web to avoid getting entangled. To detect the silk threads and recognize which side of the web the spider is sitting must surely be the ultimate refinement of sonar. Mexican free-tailed bats. They form some of the biggest and the densest assemblages of mammals to be found anywhere on the planet. There are 12 million of them in this one cave alone. But where does such a vast number of individuals find enough food within reasonable flying distance of where they roost? That was a puzzle which baffled people for a long time. But now we're beginning to discover what they feed on and where they find it. And it's very surprising. A few years ago, pilots flying above Texas reported seeing bats at high altitude. Scientists investigated and made an extraordinary discovery. As I climb into the evening sky, the weather conditions seem good. But the local weather radar shows a storm nearby growing with alarming speed. However, I needn't worry. This is not a storm, it's the bats we've just left, leaving their roost. They start from a number of points. Each is the mouth of a different cave. The swarms are vast, with up to 20 million bats leaving a single entrance. Some fly low over Texas, but curiously, most start to climb.
So that weather radar is another example of a signal processing device. Of course, there's a lot more to the weather radar than just signal processing. There's a lot of physics, of remote sensing physics involved. But one of the core pieces of the weather radar is signal processing. So this clip, the thing I like about this clip is it touches on a lot of points related to signal processing and the kinds of things you will learn in this class, and if not in this class, then certainly in 120 and beyond.
At 10,000 feet up, bats are so widely dispersed that it's very difficult to see them. But I've got with me my bat detector. And there's one. And what is more, that is a feeding buzz. So they're eating something. The question is, what? They're already a kilometre above the ground, and most are still climbing. But now the radar picks up another front blowing in from New Mexico, and the bats are flying towards it. What could there be to attract them to these great heights? Scientists find out what's flying high in the sky at night with a device.
High-tech device.
Moths. Vast numbers of these insects use the prevailing winds at altitude to travel up from the tropics to feed. Bats climb up to 3 kilometers into the night sky to catch them. Bats are so numerous and so voracious that the individuals in this one cave below me eat 120 tons of insects every night. So, if bats have such rapid...
Because of the time, I will skip this last part. I won't cry. Get the DVD. So far, I've been talking about applications where we're mostly concentrating on signal processing aspects. Of course, there are systems involved anytime you talk about processing signals. But the next clip I want to show you is actually quite fascinating. It's about fireflies and how they synchronize their flashing in Southeast Asia, in the mangrove forests there. And again, David Attenborough is going there and filming this. Interestingly enough, this is a phenomenon that was discovered in the late 19th century by Western travelers who went to Malaysia and Thailand and saw this phenomenon in person. And they came back and they've been modeling this, coming up with mathematical models of this. And oddly enough, in the 1990s, the engineers actually managed to solve a vexing problem with the internet where you had routers forwarding data, routing data synchronously causing a huge traffic problem on the net. So in that case, the goal was to desynchronize the routers so that you wouldn't hog all the bandwidth simultaneously, bringing down different nodes on the network. And it was the modeling of the fireflies that actually helped them do that. Now let's go to the fireflies.
Sound is not the only way of communicating at night. When the sun goes down here on the tidal rivers of Malaysia, the trees on the banks become alive with animals communicating with light. At first, there are just a few twinkles in the branches, but about 3/4 of an hour after sunset, the show begins.
Each of these blobs is actually a whole colony of fireflies. It's not just a single firefly. So they're already flashing in their small neighborhoods synchronously. But then after a while, different neighborhoods become synchronous.
These are fireflies, thousands and thousands of tiny beetles, only about 5 millimeters long, each sending a message in Morse code with a lantern in its hand. All those that are flashing are males, and their message, of course, is directed to the females, and it's a very simple one. Come hither, mate with me. This particular species, as well as one or two others here in Southeast Asia, reinforce that message and make sure it's sent the farthest possible distance by all flashing in perfect time together, in perfect synchrony. And the result is that even after I've drifted many yards downriver, looking back, I can
Look at how they're synchronized now, entire segments.
This display continues throughout the hours of darkness every night of the year and extends for miles along the river. The combined light of all these tiny beetles is so bright that fishermen out at sea can use them as navigating beacons to guide them back to their home rivers. Only in Southeast Asia do fireflies coordinate their flashings in this spectacular way. Elsewhere in the world, fireflies operate independently, each beaming its own individual invitation to mate.
So most likely in 120 you will learn the mathematics behind this kind of synchronization. In particular with regards to two oscillators. You can think of each firefly as an oscillator. It flashes periodically. And then when you have two of them next to each other, one tries to adjust itself with the other one. And there are mathematical equations you can write. Actually, can we turn on the camera again, please? So before we close, I want to give you a fun example. One of the things I want you to keep in mind is that what I'd like you to learn, the kind of skill I want you to learn is how to look at the world around you and break things down, simplify things in a way that you can model them and figure out how things work on the back of an envelope. So that's a high-level goal that I have for you. And it's very different from what you're used to. And I mentioned this last time in class. In high school and also in a lot of other courses in college, the emphasis is on giving you a set of formulas and then asking you to plug in numbers and arrive at an answer. That's not what this course is about. So let's do this example. This example is from Steven Strogatz's book. called Nonlinear Dynamics in Chaos. The title is very scary, but it's actually a very readable book. The way I presented is slightly different. So we have Romeo and we have Juliet. Okay? Romeo is R and Juliet is J. And they have a very odd relationship. Some of you may relate to this. Whenever Romeo inclines toward Juliet, Juliet pulls back. Okay? And when Juliet pulls back, Romeo gets discouraged and dejected. So Romeo pulls back. You with me so far? How many can relate? No. When Romeo pulls back, then all of a sudden, Juliet finds him strangely attractive. So Juliet starts showing interest. And when Juliet shows more interest, Romeo shows more interest. Okay? Let's model this. So we have Romeo. Let's start with this. Romeo starts inclining toward Juliet. Okay? This causes Juliet to pull away. So her interest in Romeo decreases. So this upward arrow is Romeo's interest increases. That leads to Juliet's interest decreasing. When Juliet's interest decreases, what did we say? Romeo does what? Loses interest. It gets dejected, so pulls back. When Romeo pulls back, what does Juliet do? Shows increased interest. And when Juliet shows increased interest, what does Romeo do? Shows increased interest. Congratulations. You've got an oscillator. Okay? That's an oscillator. And you can actually model this mathematically. So notice I haven't written a single equation. Okay? This is the back of the envelope. I described the scenario, and this is what you write in the back of the envelope. And with this simple diagram, this is not in Strogatz. This is my visual representation of this. With this simple diagram, you have cracked the fundamental behavior of this system. Some of the most exciting PhD oral qualifying exams at MIT when I was a graduate student there were of the kind where they would give you, for example, a circuit, an electronic circuit, and they would say, this actually happened in my exam. But I wasn't the only one who got this kind of question. They gave me a question, they gave me a circuit, and they said, without writing a single equation, write down the natural frequencies and the dynamic modes of this circuit. That's hard. And you need to be trained to do this kind of qualitative, intuitive analysis to stumble on the answer. And it's very difficult at the beginning. But it's a skill that I encourage you very strongly to try to develop. So, let's see. I have about a few minutes. Let's try to model this. So, let's say R as a function of time is Romeo's interest in Juliet. So Romeo's instantaneous interest in Juliet. Okay? And J of t is similarly defined. Similarly defined for Juliet. with r dot of t, we mean the time rate of change of Romeo's interest, the slope of his interest, the slope with respect to time. Okay? And similarly, for Juliet's interest. A very simple model of this scenario is that Romeo's interest increases so let's put linearly with Juliet's interest. Now, according to so if Juliet's interest doubles, Romeo's interest will also double. Can you tell me, based on the description of the story, whether B, the constant B, has to have a positive or a negative sign? Look at the top row. Oh, I'm sorry, the left column. When Juliet's interest increases, Romeo's interest increases. So when Juliet shows a positive interest toward Romeo, Romeo's interest increases. Its time derivative is positive. So B must be positive. Okay? What about Juliet? The rate of change of Juliet's interest, let's say it's linearly related to Romeo's interest. Constant C, what's the sign of the constant C? Negative. Okay? You will learn probably in 120, because I don't think we'll have time in 20 to get to it, when you study state-space systems, that you can write this in matrix vector form. R dot of t, j dot of t equals 0, b, c, d. Oh, sorry, 0, b, c, 0. And the properties of this matrix determine the dynamic behavior of this particular system. This is a two-dimensional, linear state-space system. And all these buzzwords should not have any meaning for you whatsoever. The point is, there's a mathematical model for this particular scenario that I described. Now, how do we get to this cyclical behavior? We got to it on the back of the envelope in that crude way. But can we also describe it using these two equations, viewed individually? So let's draw a plane. In one axis, I put R, or R of t. In the other axis, I put J. Okay? Let's say I start here. Okay? R is 0. Okay? This axis, the vertical axis, is where R is 0 at the particular time I'm looking at. You with me? What can you tell me about J? Is it going up? So if this is a particle moving in this plane, I want to figure out which way this particle moves. The particle represents the state of the system at a particular time. So I'm at some arbitrary time, t. Okay? I'm here. Romeo's interest is 0. He's neither inclined nor disinclined toward Juliet. Which way does this particle move? Does it go up, down, left, right, northeast, southeast, northwest, southwest? Think about it. R is 0. So what does that tell you about the time rate of change of J? So can it go up or down? Can it have any inclination toward up or down? So J, this particle is going to move horizontally. Instantaneously, if I want to put an arrow, it'll be either to the right or to the left. Correct? Which is it going to be? Is it going to be to the right or to the left? To the How do you figure out if it's to the right or to the left? Huh? J of t is positive, B is positive, so R's at epsilon seconds later, R's interest is going to be greater than his current interest. So the arrow is to the right. Okay? Now, if I start off here instead of here, would the arrow be larger or smaller? Smaller. Okay? So let's go here. J is 0. Which way does R move? J is 0. Is R going to move to the... So can it move to the right or to the left? No, because R dot is 0. So you look at the next equation. R is positive. C is negative. So J dot is negative. So which way is the arrow? Down. And you can do this analysis like so, graphically. Notice, I have, aside from these two equations now, I haven't written nothing. And you can imagine that the behavior is elliptical. When would the so now you have an idea of, if I give you what the state of the system is, where R stands and where J stands at any given point in time, you should be able to tell me on which one of these trajectories the particle is going to move. And you can see the cyclical oscillatory behavior from this visualization. And what else can you... oh, here's another question. Again, back of the envelope type of analysis. Under what conditions would these ellipses turn into circles? When B and C have the same magnitude. That's when you don't have any bias in the horizontal or the vertical direction. Go away. I'll see you next Thursday. Oh, huh?